have a very nice tutorial from a very nice set of people from 3 different institutes. And the topic is going to be learned query optimizers at the forefront of the AI-driven databases. So this is a very exciting topic, and this is going to be organized in a total of 2 hours with a break in the middle after the first hour. And there's going to be a question and answer session at the end. So having said that, I think that we are all set. This session is recorded for your information, and it's going to be put online on the EDBT website later on. Ron, I think that we are all set. If you are ready to start.
Okay.
Go ahead.
Okay.
Thank you.
Let me share my screen. Okay. 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 A moment. Let me share my screen. Okay. Okay, so can you look at it? Can you see it?
Yeah. It's good.
It's good. Okay, so let me start. Okay, welcome everyone. Thank you very much to participate our tutorial. Today we will talk about the learned query optimizer at the forefront of AI-driven basis. Well, this tutorial is organized with all of us, and this is our speakers. Today we have I am Rong Zhu from Alibaba Group. Today we also have Ziniu Wu from MIT and Cheng Liangchai from Tsinghua University, and my colleague Andreas Pafford from Alibaba Group. The 3 other authors will not speak today: Bolin Ding, Guoliang Li, and Jinren Zhou, but they are also contribute to our tutorial. Well, okay. First, as outline, this tutorial would have we will have 2 parts, and each part, part A and B, will last for 1 hour. In the part A, we will talk about some preliminary information and the learned individual component in Query Optimizer and some techniques for the learned whole QU modular. And in part B, we'll talk about some applications and deployment and a summary and the future work. And then the time is left for Q&A. Well, okay, now let me start. Well, first, in the first part, preliminaries, let me introduce a bit on Query Optimizer and learned QU. Well, for Query Optimizer, it is a central place and central role in DBMS. Its role is like that. On a data D with a query Q, it needs to generate a physical plan P for the plan execution. So it directly relates to the system performance and decides the system performance. So its role is very important. However, Query Optimizer is a very difficult task. This is because for each SQL query, we may have different join orders. For example, in such a simple example, we have 2 join orders. And on each table, single table, we have different scan method, thank scan, index scan, and other. And for each join table, we have different join method: merge join, hash join, nested loop join, and etc. So we may want to know which plan is better. Well, traditionally, Query Optimizer follows a general volcano framework, where it may consist of 3 main components in this module. Well, the join order selection part enumerates all possible candidate plan, meaning all possible join order for the query queue. And then the cardinality estimation part will try to estimate the number of tuples for each subquery, and then you know for each candidate plan in join order how many tuples you accessed, and then you use a cost model to estimate the running cost of each subquery using different scan or join method. So you can estimate the cost of each plan P, and then using this workflow, you may identify a good plan with the minimum estimated cost for execution. For this example, we may know that the estimated cost for each subquery listed the number here, and then we know the join cost and scan cost of each operation. Then we could identify such a plan may be much better than others. Well, this is a traditional framework, but these traditional methods are not favorable enough. For join order selection, we may using dynamic programming or greedy search. For cardinality estimation, we were using some simple statistical method, such as histogram sampling. For cost model, it may all ruler-based and turned by our experience. Well, we can see that all these methods are driven by experience. It's not very accurate and fine-grained turned, so may not have good performance in all cases. Well, recently, we witnessed that learned query optimizer techniques may be provided more better performance, and QU query optimizer has been a suitable experimental plot for learned techniques. For example, for join order selection, it is a decision-making problem. We may using multiple reinforcement learning techniques. For cardinality estimation, we can use unsupervised models to model the data to estimate the cardinality. For cost model is ruler-based. We can automatically learn it by supervised ruler learning methods. So these learned techniques may be more automatic, fine-grained, and accurate solutions. So we have witnessed a progress of advances recently on query optimizer. We have witnessed more than 100 papers published recently in this area. So query optimizer has been a pioneer in AI for DB and beyond. So its features needs to have a deep analysis, a deep compression, and benchmark analysis. We also witness many future research opportunities in this field. That is why we organize this tutorial. We want to introduce from both the learned component, each component, and then the learned E2E query optimizer, the whole modular and its applications, and in real-world scenarios and the system deployment tool. Finally, we want to target an intelligent and practical query optimizer. Now we start this journey together. Well, first, in the second part, let's introduce the techniques for each learned query optimizer component. First, we start the cardinality estimation. This part will be introduced by Zniu Wu. Now let's wait for Zniu Wu, okay?
Yep. I'm ready to share my screen.
Okay.
Yeah, thank you, Ron, for this very good introduction. Okay, can you guys see my screen?
Okay. Yes, okay.
Yeah, so cardinality estimation aims at estimating the result size SQL of a query queue without its actual execution. So it learns a solid foundation for the cost estimation and also the join order selection. Let's see a simple query here containing joining of 3 tables. So if we can accurately estimate the intermediate join size of A join B to be 100 and B join C to be 1000, then we can accurately select the join order. So the first join order of A join B first, then join C is more favorable. So it's the estimation accuracy of cardinality estimator directly determines the query plan quality, and the inference speed directly affects the overall query runtime, because a slow cardinality estimator may introduce some large latencies. And its model size, training speed, and updating speed are also very important aspects for system deployments. Let's see the existing works on cardinality estimation. We can roughly categorize the existing works into 4 categories. The traditional method includes histograms and sampling. They are widely used in the past decades, also currently widely used in DBMS. So until recent, we have witnessed the machine learning techniques has been used to solve this problem. This includes the learned data-driven method, learned query-driven method. So learned query-driven method analyze the query workload. So it learns the regression model that directly maps the query queue to its cardinality, CQ. The learned data-driven method, instead of analyzing the query workload, it analyzes the data and build distribution models to model the probability distribution of all attributes A on a table T. And then the Carnati can be easily calculated as the probability of a filter predicates Q on table T multiplying by the total number of rows in T. There also exists a method, a Carnati estimation method called bound-based method. So instead of estimating the Carnati, it provides the upper bound on the Carnati. This can avoid really expensive joint orders because it basically assumes the worst case of a Carnati. It can also avoid very expensive physical operators. In experiment, it has been shown that it can generate effective queries, but their estimation latencies are sometimes unaffordable because they need to materialize each single tables in order to handle the case of joint. But rigorously speaking, the bound-based method are not technically Carnati estimator because it does not estimate a Carnati, it provides the upper bound. So we will not explain too much detail of this method in this tutorial. Let's go through the details of all other three categories. The traditional method are most widely used in modern DBMS. It includes histogram and sampling are the most popular method. Histogram method use attribute-independent assumptions to decompose the joint distribution of multiple attributes into the product of each single attribute distributions. In this way, it essentially decomposes the complexity of exponential distribution into the complexity of only one attribute. So apparently it has fast inference speed, low storage cost, but it can generate high estimation errors because in real world, the correlations generally exist. This will lead to suboptimal plans. Some variants of histograms includes multi-dimensional histogram, query-driven histograms. They can capture the attribute correlations in certain degree. However, their estimation accuracy is not still satisfactory enough. The next popular method is the sampling method. The idea is quite simple. They execute the query on a smaller sample and divide by the sample rate to get the estimation on the real Carnati. It's apparent that its estimation accuracy and inference speed can trade off because we can always use a larger sample for more accurate estimation. However, a larger sample would cause slower runtime. Certain variants of sampling method includes the kernel density estimation and also some sampling bit method on the joints. So up to now, we have explained how the traditional method works for each single tables. So in the case when they handle joints, they generally adopt the joint uniformity assumptions. A simple case would be joining two tables, a query Q joining T and R. And Q, we denote QT and QR as the single table filters. And the Carnati of a Q can be written as a product of the single table probability of QT on table T, the single table probability QR on table R, and multiplied by the final joint size of T joint R. So basically assuming the joint keys are uniformly distributed. Also, there exists some biased and unbiased sample-based method for joints. I will not explain in details. So the learned query-driven method builds supervised method to supervised model to map query Q to its Carnati CQ. It contains two important parts. The first part is the query feature engineering. Basically includes how to turn a SQL query into an array of values such that the supervised machine learning model can understand them. A simple example here, basically they featureize each of the table name, each of the column names as a one hot vector, and they featureize each of the joins as a bitmap, and also the future predicate as a column ID concatenated with the normalized value. With this set of features, they input all this set of features into the supervised methods, such as the XGBoost, neural network, TRIA-STM, deep ensembles, and they train this network in order to output the desired Carnati. It has fast inference speed because each inference only takes one path of the neural network or other equivalents. It's also very versatile as this feature engineering method can really work with different join patterns, self-join, cyclic joins, and they can also support different filter types, like even the complicated ones, disjunction, string-like, and user-defined functions. However, its estimation accuracy is highly dependent on the training query workload. It generally requires an excessive amount of training queries to attain a reasonably good performance. We are talking about 10,000 or hundreds of thousands queries, which are generally not available for a new database. And its performance also degrades severely if the data or the workload changes because their models are fixed on a fixed workload and also a fixed data. The learned data-driven method are more flexible in a sense of deploying it to a new database or in case of the data change or workload change. Basically, they do not analyze the query workload. They build statistical model to capture the data distributions, the probability distribution of all attributes within a table. Certain statistical model includes deep autoregressive model, probabilistic graphical models, and normalizing flow models we will explain in detail. So these are the techniques to build single table distributions or the denormalized table of the join results. However, in order to handle the general case of join, they use fan-out method to handle the join queries. So fan-out means each tuple in a table can appear multiple times in the join result. So in order to account for the effect of joins, they generally store an actual columns called fan-out columns in their data and learn that distribution of that fan-out column with the other attributes that's already appears in the table. This method generally produces very accurate estimates. So the learned data-driven method achieves the current state-of-the-art performance in end-to-end query performance. So let's see some distribution modeling techniques. The deep autoregressive model fully factorizes the distribution. So basically for a table T with attributes A1 all the way to AN, it can be decomposed as n conditional distribution following the chain rule. We can say there is no assumptions made here. This is just based on chain rule. So it captures all the correlations within all these attributes. So it has high accuracy, but it can have large model size in order to capture all the complicated distributions. Also, the inference speed can be slow. Bayesian network is a very popular method in the statistical machine learning. Basically, each Bayesian network comes with a directed acyclic graph that models the causality pattern of all attributes within a table. So basically, the causality graph means the parents causes the children. And based on this Bayesian network, the distribution of all attributes can be factorized as a product of lower dimensional attributes. So all attributes are conditionally independent of other attributes given its parents. These conditional independent assumptions are widely present in the real-world data, so it still has high accuracy. Also, the models are explainable and more compact. However, in order to learn such directed acyclic graph is considered a very hard problem. And a recent work, BaseCard, addresses another hard problem of Bayesian network, which is how to calculate the probability efficiently. They basically introduced the JIT-compiled variable elimination and the progressive sampling method for estimating the cardinality. So to summarize, the Bayesian network, especially the BaseCard, have high accuracy, small model size, and fast inference speed, but the training time can be slow. Another distribution building technique is sum product network used by DeepDB. They have local independent assumption in a sense that they split the data by rows in order to find local independence between attributes. And when such independence is found, they build a one-dimensional histogram to capture this distribution. Its accuracy, inference speed, and model size are in general pretty good, but in the case of highly correlated attributes, their models can blow up and also accuracies will decrease because it's very intuitive to see if two attributes are highly correlated. No matter how you split the data by rows, these two attributes will never be considered independent. So building upon this insight, the factorized sum product network used by a recent work of ours, FLAT, they combine the techniques from Bayesian network and sum product network to adaptively process highly and weakly correlated attributes, in a sense that it does not have the drawbacks of DeepDB, but it can also estimate it can also achieve high accuracy with a small model size. But its inference speed can sometimes slow for a large amount of attributes. Normalizing flow method is a newly proposed Carnati estimation method. Basically, the normalizing flow model understands the continuous distribution. So the phase method dequantizes the discrete attribute to ensure continuity and build all the attributes together. This method generally have high accuracy, fast inference speed, and compact models. So let's see some benchmark evaluations of all aforementioned representative works. We have two evaluation benchmarks here. First is the IMDb Job Light benchmark, which is a real-world, which contains the real-world data with complicated distributions. So the schema contains 6 tables. They form a join, a star-shaped join. And we also built a new benchmark in our recent BLDB benchmark paper called StatCEB. So this benchmark also uses the real-world data grabbed from the Stack Overflow website, also with very complicated distributions. As we can see, the join schema is more complicated than the IMDb Job Light, and also we have more tables and more attributes. So for end-to-end evaluation, we integrate all these methods into Postgres and evaluate their end-to-end time on these two aforementioned query workloads. We present its end-to-end query runtime, which is the total runtime on all the queries in the query workload. Execution time is the pure execution time, and planning time is basically the latency caused by each of the Carnati estimation method. We also provide the relative improvement over the Postgres baseline here. Also, the true card here means injecting the true cardinality into Postgres. This basically represents the optimal performance a Carnati estimator can ever achieve. It does not correspond to any of the real Carnati estimation methods. So to summarize the result, we can roughly say the traditional method has barely have any improvement over Postgres and even performing worse than Postgres on both of the benchmarks. The bound-based method, we will not explain in detail, but we can see its execution time is quite good, but its planning time is very slow. So it's not suitable for some short-running queries. The query-driven method generally performs slightly better than the Postgres, mainly because they really need a large amount of training data, and which might not be available. So the data-driven method achieves the state-of-the-art performance. It can significantly outperform the Postgres baseline. And in the end, we also have a query plus data method. Basically, this method learns from both query and the data. However, it performs relatively the same as Postgres. Okay, so to summarize, we found that the traditional methods are most general, lightweight, fast to train and update with very low latency, thus perfect for system deployment. However, its estimation accuracy can lead to unsatisfactory query plans. The learned data-driven method have the state-of-the-art performance, but they are less general in a sense that they cannot effectively handle string-like queries or user-defined functions, and they can sometimes have large model or slow inference. The learned query-driven method are perfectly, it's going to perform well for static DB instance, but they are not suitable for a new database or databases that can have frequent data update or workload shift. That's our main takeaway for the learned cardinality estimation component. So we will give the talk to Cheng Liang. Yeah.
Hi, can you hear me?
Yeah.
Okay, I can hear you. Okay.
This is my first time using Zoom, so
okay. I think you can start. Okay.
Slide. So let's come to the cost estimation and joint order part. So cost estimation aims to predict the resources usage of a physical execution plan for a query, including the I/O usage and CPU usage. It has close relationship with the cardinality estimation. Even we can say that for the traditional cost estimation methods, they utilize a cost model built on the estimated cardinality to incorporate some physical operators. Compared with the estimated cardinality, the estimated cost provides more direct running overhead for guiding the plan selection. But the cost is harder to estimate than cardinality because you have to consider many multiple factors, such as the sequential scan cost or CPU usage. So we categorize the current learn cost method for two categories. The first one is estimate one query without considering the others. So compared to the cardinality estimation, it is an end-to-end way that takes as input the query encoding and output the cardinality. So this can be regarded as a regression problem. So the second one considers the correlation between multiple queries, which use a graph to represent the correlation between plans and use a network to predict the cost. It's also something like a regression problem. So for the single query cost estimation, there are several challenges. So the first is we need to build an end-to-end model to do the cost estimation to avoid the accumulated errors of the cardinality estimation. The second one is the learning model should capture the tree structure information of the query plan. And the last one is how to encode the predicate. So I will introduce the tree LCM method that can address the above challenges in an end-to-end way. It learns a representation for each subplan with physical operator and the predicate, and outputs the estimated cardinality and the cost simultaneously by using another estimation layer. Moreover, the method encodes the keywords in predicates by using the word embeddings. So the query performance prediction problem has been studied for 4 years. However, it is challenging to predict for concurrent queries. First, the queries may have complicated correlations that can significantly affect the performance, including the buffer sharing, the data block, and the resource pools. There are and the resource computation between any operators can be executed together. Besides, the database configurations can also affect the query performance. For example, two-phase locking can take much more time than the general locking. And some system parameters like the memory or I/O control can also affect the performance significantly. So in short, the query operators and their correlations and configuration constraints actually form a graph model of various structures. So we need to predict the performance on the graph model using both the query and database features. So let's first see how to construct such a graph model for performance prediction. This procedure includes 3 main steps. First, for the queries issued by the user, we use the database optimizer to obtain the query plans. And second, we extract the operators in the plans as the vertices of the graph. Then each vertices contains 4 features, including the operator type. It can be sequential scan, update, aggregate, or anything else. And then next, we capture the correlations between operations at edges. The first is the parent-child relationship in every query plans, which can reflect the data flow from the child node to the parent node. The second is the data sharing relationship for the read operators using the same data or index or intermediate tables. And the third is the data conflict relationship from the early write operators to the other operations that can access the same table. And finally, the resource computation relationship for the concurrent queries please note that the ages are potential factors of the query performance. So how do we decide which ages can really take effects and how to encode them? So to solve the problem in this work, we can use the graph embedding to encode these vertices based on the graph structures. In each layer, the procedure of graph embedding can be represented by this function. So the E prime is the sum of the age matrix and the identity matrix, and W is in the network. W in the network shares the global by all vertices, and H is the output of the last layer. For the first layer, H is the vertex matrix. D is the neighborhood matrix that captures the adjacent vertices of every vertex. In this way, we can efficiently predict the performance of concurrent operators from this graph and easily infer the concurrent query performance. So for example, the total execution time of a query equals to the finish time of its root operator. So next come to the join order selection. So given a cycle query, a join order is captured by a binary tree in which each leaf node represents a base relation. It plays a very important role in database optimizer, which has been studied for many years. So traditional methods typically search the solution space of all the possible join orders with some pruning techniques based on the catalytic estimation and cost models. So the dynamic programming-based algorithm often selects the best plan, but it has very high computational overhead. Also, the generated plan by the dynamic probing algorithm may have large cost due to the wrong cost estimation. So some heuristic methods such as the genetic optimizer, the quick pick algorithm are proposed, but they may generate plans. They may generate plans more quickly, but they can, some poor plans may be generated. So we need the learning-based join order selection algorithm. So we also categorize the current learned join order selection into two categories. First is offline learning methods. It predicts based on the previous workload using the reinforcement learning based methods. The online learning methods do not need workload and the plan of a query, which can be changed during the plan execution. The query can switch to another plan if it finds the current plan is bad. So it learns when the database executes the query. So let's first see the offline learning method. The challenge first is how to reduce the huge search space of all the possible join orders. And second one is how to select the best join order among all the possible ones. So the reinforcement learning naturally fits the join order selection problem. So as we know that the reinforcement learning consists of many factors like the agents, the action, environment, reward, and state. So in the join order selection problem, the agent can be the optimizer, and the action can be which table joined to another which one. And the environment is the database. It can provide the reward such as the cost and latency. And state is the join order. So let's see the right part. So there are many states. So we have the initial states. There are many tables that are not be joined. And we have a terminating states and all the tables are joined. And there are some intermediate states. So the reward can be given by a database, and we can learn some knowledge from the reward. High reward means that this is a good join order, and it can lead to a very efficient plan. And so the reinforcement learning is a exploration and exploitation trade-off. So we can learn from to generate the we can learn to choose the best action in each step and finally produce a well-performed plan. So, but the naive reinforcement learning method like the rejoin, it has many, it has still has some room to improve. So there are three main challenges. So the first one is the intermediate state of the reinforcement learning is a forest. So it is hard to represent. So for the the rejoin method, so for different plans, so like this figure, for different plans, they may generate the same representation. So this is not a good choice. So so we should so the RTOS, this method is proposed to solve this problem. It's use the tree LSTM to encode the query. So different structures of queries lead to different representations. So the model can capture the structure of the query plan. And the second challenge is the training time is huge when we want to collecting the latency as feedback. So the previous method uses the cost as feedback, but actually we want to optimize the latency. So the ideal solution is to use latency as feedback. But if you want to use latency as feedback, it may cost it may consume a lot of time because you have to really run the query. And the third one is the schema change leads to the retraining. So so the schema often changes, so you do not want to retrain the model every time. So we propose the RTOS. This method uses the tree LSTM-based Q network. It uses an array to represent the subtrees and uses a child sum to represent the forest. So, so using the tree LSTM, so we do not have to worry about the different query plans leading to the same representation. So, so in this situation, different query structures lead to different representations. So you can capture the structural information of a query. So the second one is that it uses two-step training. So it uses the cost to pre-train the model and use the latency to fine-tune the model. So it is a trade-off between the accuracy and the efficiency. So the cost, the training use cost is fast and it's not accurate enough. So you use latency to fine-tune it. And last one is use the dynamic neural network. It uses the DFS to build the neural network for each plan. So even if the schema changes, so you can, but you can still do not need to retrain. So let's come to the next part. So in real world, the workload in the database is constantly changing. The data, the drawing graph, and the schema may change. The previous learning optimizers can hardly continue to give plans and require fine-tuning or even retraining. So in order to avoid the above problems, the Skinner DB does not maintain the data statistics and uses simplifying cost and cardinality models. Instead, it learns near optimal left deep query plans from scratch and on the fly. So during the execution of a given query, so they can change their plan. So there are two challenges. The first one is how to design a new working mechanism that allows the optimizer to learn and switch between different drawing orders online. And the second one is how to evaluate and choose different drawing orders online. So unlike general database can only execute one plan for queries, Skinner DB use EDBT style approach. It divides the execution of a query into many time slices. Each time slice can choose a drawing order. So within each slice, it uses an array drawing method to execute the drawing plan to support combining the results of previous time slices after plan switching. The selection of drawing order of next time slice depends on the effect of each drawing order in the previous time slice. So through this approach, the Skinner DB can execute different drawing orders in different time slices and integrate the results of different drawing orders to obtain the final query results. So the next question is how to choose the correct orders in each time slice. So Skinner DB uses the percentage of queries completed a drawing order within a time slice as a reward value to this order. It uses the MCTS to balance the need of exploration and exploitation. So it can learn the performance of different drawing orders online, such that the learning method is not limited by the accuracy of the statistical information. But since Skinner DB requires the executor to be able to perform efficient plan switching, it is currently only suitable for efficient in-memory databases. So let's compare the different kinds of drawing order approaches. So we can see that in terms of the quality, we can see that the offline optimization method is better than the traditional method and the online optimization methods because it can see many training examples. So it has high accuracy, but it is not adaptive because if the workloads change, for example, the dynamic workloads, so it cannot handle the out of distribution problem well, but the online optimizers can and do it well. So you can choose different methods in different scenarios. So in summary, for learn cost estimation and the drawing selection, they work together to generate an optimal plan. So the drawing order selection selects a good order based on the cost estimation method. So they both can be optimized through machine learning techniques. So the cost estimation can use the neural network to encode the query, and it can be regarded as a regression problem to predict the cost. And it is somewhat similar to the coordinated estimation method. So often they can, so you can use the cost estimation method to solve the coordinated estimate method problem. So the drawing order selection mostly relies on the reinforcement learning methods because the database can provide feedback as a reward, and it can be seen as a decision-making process step by step. So it's that you can select one table to draw after another. Which can be regarded as a decision-making process. So that's all. Thank you. So let's welcome the next speaker.
Excuse me, can I ask a question now, or shall we ask questions at the end?
Okay, maybe could you ask a question later? Maybe
okay,
after.
Okay.
Okay. Let me share my screen. Okay. Hey, Changliang, please quit. Okay. Can you see it?
Yes, we can see.
Okay. This part I would be responsible to talk about the following content. Part 3 on learned the Hue query optimizer module. That we discuss how to previously we discussed how to learn for each component, cardinality estimation, cost model, and joint order selection. Now we see how to learn a query optimizer model as a whole. Well, we are introducing two typical methods, that is NAIL, that is E2E learned QO, try to replace the traditional QO, and then another representative work is the BAO, that is learn how to steer an existing QO to be more efficient. Besides them, we are introducing our work, one model for all called MTMLF framework, that is may step one more than NAIL and BAO to overcome their challenges. Finally, we make some comparison and analysis. Okay, first, let's just revisit the traditional QO architecture. Well, for the NAIL, that is we learn to replace, that is we try to learn to replace the functions of the three component, join order selection, cardinality estimation, and cost model, but may not as exactly the same as them. Well, the architecture of NAIL is like this, that is all the grid parts are learned by models. Well, for a query queue, we first try to featurealization. So we try to encode this query, and then we use a based plan search. That is, the based plan search is replace the join order search. Well, the based plan search try to search for each petrol plan P prime. Well, P prime is maybe a petrol plan for query queue. And we're using a value network to estimate the latency T prime of P prime. Well, the latency T prime is not the running time of P prime, but a complete plan that is generated from P prime, but is a complete plan for Q. We know its latency T prime. We use a value network that is trained on some sample workload to estimate it. And then finally, we use this based first search to gradually enlarge petrol plan P prime using this value network to estimate its latency. And finally, the P prime grows and it approaches to be a complete plan for query Q. And we use this plan P to execution. After execution, we know its exact latency TP, and we use this to refine this value network. So it's iterate like this. Well, next, let me introduce each part with more details. For the query encoding, we need to encode both the join information and the predicates information of the query. For the join, for this query, for example, for the join information, we can encode its join graph on which table I joined with each one. And also the column predicates information we can use in one hot or embedding methods to encode each attribute, the predicates on each attribute. By concate them together, we obtain the query level encoding. Okay. The next is on the value network is how we for the value network, we are training using a model to learn the latency of the based percival plan from the petrol plan. The based percival plan is a complete plan for the query. Well, we all know that the plan for query is a tree structure. So in fact, the value network uses a structure called tree convolution. It is in fact an inductive base of what we know for the query. Well, tree convolution means that we just directly model the plan as a tree structure, and we using some ways to carve the information in a bottom-up way. During this process, then we could know which we could automatically train it to identify different ways for different operation, different operators for different join orders, and we could identify different information. Well, for example, here we can see that on the up example for merge join and hash join, they have different encode, and then they will have different weights. And in the underlying example for the different join order AB or AC, we also can learn the different weights by using the tree convolution that then tries to learn to filter weights for different operations and tables in an automatic way. Okay, by experimental evaluations, we found that it shows that NAIL could outperform or match existing commercial query optimizer or open source query optimizer with enough training. Okay, so now its advantages that it is the first climbed automatical end-to-end land QU, but it has also many disadvantages. First, you know that Nail tries to learn everything by itself using the encoding of the queries to learn the value that work. So it has a very, very long training time to converge and a heavy code start. You need to wait a long time to wait it that to be trained has a similar performance approaching an existing query optimizer. And its featureization is very ad hoc for each database, for each DB. So it is low, has low generalization ability, and it's very, very hard to update. And Nail is trying to replace, but not to modify an existing query optimizer. So it's a waste that you cannot reuse existing DBMS's codes, and replace a QU in existing DB may be also risky. So next solution is BAO, that is try to steal an existing QU, but not to replace it. For steal, we know that each QU may have different hint sets. For hint set, it means that you can disable or enable certain types of operations. For example, you can disable the nested loop join in the Postgres. Well, for each query, if we turn a good hit set, it may help us to generate a good plan. This is because a bad plan is often generated because we have some estimation errors in cardinality, and then we choose a bad operation. But if we just disable the bad operation for this specific plan, then we may have chance that the query optimizer just tries another code path, and then it is possible that it could generate a good plan. So this is idea of the BAO. Here is the architecture of BAO. That is, we have an existing query optimizer, and for data D and a query Q, we have a hint set that has different hints. For each hint, we into the existing query optimizer, we will have a corresponding plan, and we will have different plans. And we also here train a plan latency prediction model that can be used to predict the latency of each plan. Well, across them, we choose the plan P with minimum estimated time, and we use it for execution. After execution, we also use its latency TP to refine this latency prediction model. Okay, the latency prediction model also use a similar tree structure and the convolution operations to Nail. It is also an inductive bias of what we know for the tree structure of queries. It can identify the difference of using different join orders, different scaling and join methods, and learn the filtering weights automatically. Well, by evaluation results, BAO could largely outperform the open source DBMS and the commercial DBMS on different data sets. Here is its performance from on the Postgres and is the difference with the optimal plan on the JOB job query workload benchmark. Okay, now we can also see that the difference between Nail and BAO. We can see that Nail could overtake BAO after a very long time of training, because we know that BAO just turn in the hit set to generate a different plan. So its search space, or we call it freedom, is not as large as Nail. Nail can generate any plan if it is valid, but BAO, it can use in turning hit set, so it cannot touch some plans sometimes. So its performance ceiling is a bit lower than Nail if Nail is trained a very, very long time. But BAO also converges fast and easily adapts to dynamic workloads because its training space is very smaller. You do not need to learn everything by yourself. You just learn how to map a query to its latency. Okay, but not a Petro query, because for a Petro query, it may correspond to many different complete plans. Okay, so BAO's advantages is that first is try to steal, but not to replace. So it's easy to deploy, and we can reuse the existing QU, and it's also easy adapts to any update. So its generality is better. And as I have mentioned, it has smaller training time than Nail. But Bao's freedom of plan search is a bit lesser than Neo, so its performance maybe have some loss sometimes. And Bao still has a cold start and regression problem. You cannot get a good enough learned query optimization at the very front. Okay, so we just could compare their performance here. We compare them from different aspects. First, whether the learning space and whether the need card is cost model, their plan search and method and plan search freedom, and the training time, whether they could have updates, code start or deployment easily. We can see that both of them have some advantages, but also have some disadvantages, not very satisfying. Well, we can summarize here as here, we can see that Neo is converged very snowy, but it could gradually approach as optimal if we train very long time. Neo's performance ceiling is a bit lower. It has less freedom than Neo. This is Bao, but it converges fast. Both of them cannot need a long time to approach the performance of an existing queue. This is called cold start or regression problem. What our goal targets is maybe at the very front, we can stand at the similar bar of an existing queue and then gradually train fast to approach the optimal plans. But how to approach this? Okay, let me tell you in the second part. I think it's time for our break. Okay.
Thank you guys for staying perfectly on time. So we're gonna have a 14 minutes break, and we're gonna resume the tutorial after these things. Okay. I remind you that there is a question and answer long slot at the end of the tutorial. See you in a few minutes. The session 1 minute. Welcome everybody. This is the second part for the first tutorial. Learned Query Optimizer at the forefront of AI-driven databases. We're going to have another 30 minutes of presentations from the speaker, and then there's going to be about 30 minutes for question and answer. So, Long, if you want to start sharing your screen.
Okay. Okay, can you see
Excellent.
it?
Yes,
okay.
Go ahead.
Okay. Okay, let me just continue to see that how to achieve our goal of the performance queue of this desirable query optimizer, which could start with this performance close to an existing queue and gradually trained to be more optimal. So we make one step out. That is, we note that we propose a model called MTMLF, one model for all. We know that the learned knowledge is decomposable. Well, on the data level, we see that we can divide it into data-specific knowledge, that is, which is unique to data, including the workload and the data distribution. Also, the data-agnostic mental knowledge, which is common rulers across different DBs, and it is summarized by expert experience and some rulers. Well, on the task level, we also have some task shared knowledge, that is data and query representation used in all tasks. In these three tasks, cardinality estimation, cost estimation, and join order selection, we also have some task-specific knowledge, that is method to how to slow this specific task. So our method is to using shared learning and specific adaptation. That is, on the task level, we can using the we can just represent the general and data query in a general way that could benefit for our task. And for task-specific knowledge, we're using a small model to adapt to each task. On the data level, for each data-specific knowledge adapt to each DB, we can try to fine-tune a large pre-trained model. And for the data agnostic mental knowledge, we can summarize from the multiple DBs and store it in a pre-trained model. Well, so in our MTMLF framework, we have divided into a service provider side and a user side. On the service provider side, we're using a pre-trained large model as services, which we store the data agnostic mental knowledge that is summarized by experts, and we access multiple and numerous DBs using such as federated learning to access them more, to see different distributions, to pre-train them and summarize them. And you again across and on top of these pre-trained large models, such as transformer, this is shared for different tasks. And we also provided some small models, pre-trained models with mental rulers to turn for different tasks. And on the user side, we just fine-tune these pre-trained models to fit users' data. We can model users' DB and queries data to turn these pre-trained models that is shared by all tasks, and then using some running queries to fine-tune the pre-trained models that is specific to different tasks. So this architecture could be more efficient treat without redundant learning, and it has no code start and regression problem because it has already using the pre-trained model with some mental knowledge. And sometimes it is a task could be more effective with some poster knowledge guidelines. For example, we can using the guidelines from cost model to contribute to cardinality estimation. So this workflow is more great contribution because it could be provided the pre-trained models as fundamental tools by some services, and it's more easy to involve, manage, and optimize. And this is the general architecture of the query optimizer that we jointly learn multiple components together. By our evaluation, we found that it is better than previously just plugging in architecture, and its multitask learning is better than separate learning. Okay, and it has some this pre-tree and Fion 2 has some ability of transferability across different data, and it can be transferable to new DBs and more effective. Okay, so just as a summary, you can see that the learned query for the learned query optimizer as a whole, the nail learn everything by itself. In time is long and generation is low and has heavy code start problem. Bao try to steal existing QU by turning its heat set. It is easy to deploy and has better generality, but it has some performance loss and remaining code start problem. We step out with our MTML framework using pre-training and fine-tuning. It's a possible routine for desirable learned QU, but we still have a long way to go to achieve the desirable learned query optimizer. Okay, this is the second part. For the first part, applications and deployment, we move from learned algorithms and models to more application and deployment part. We're introducing 2 case studies on learned cost model and learn to steal query optimizer of Scope, that is a widely used system in Microsoft. And then we're introducing the challenges of actual deployment and demonstration our startup system called Baihe, which is a general tool for deploying AI for DB models in a general tool. Okay, for the scope, let me first introduce a bit. It is a big data system for data analytics used in Microsoft. It is developed by one of our speaker, Jinren Zhou, in Microsoft. Well, for scope, many of the scope's workload consist of recurring jobs. It is using the same scripts, but on different data. This is an analysis on its cost model. We can see that there is a very wide gap between the actual and estimated cost, even with using its actual cardinality. So it is not accurate. Then we try to learn the cost model for it. First, we may see that there are different ways for the learned cost model. We can learn a single global model, but it is not equally effective for all operators. This is because different operators have very different performance behavior. And even for the same operator, its performance is different and vary dramatically with a different context. So it's not easy to learn a very accurate global model. So another solution is we may try to learn many specified smaller models, and each model is for a common operator subgraph template. Here, the operator subgraph template is some common expressions that a subgraph of operations that frequently occur in recurring jobs. We are trying to learn multiple small models for each. Here is we identify some features and using different machine learning models such as neural network, random forest, and elastic net to learn multiple operator subgraphs. its accuracy is very low, but its coverage is not high because some operator subgraphs cannot be covered if we just identify some common Oakley subgraphs. Okay, so we need to do an accuracy and coverage trade-off. Another way to solve is that we try to learn an operator level model. That is, we try to learn a model for each operator. This would have a very high coverage, but its accuracy would be poor because I have mentioned before that the behavior of operation changes with respect to the context. So it makes two trade-offs by proposing two learning methods. One is the operator input model. That is, it learns multiple models for each operator, but each for jobs just sharing the similar inputs. So it just divided the context of each operator. Another is operator subgraph approximate model. That is, we learn a model for all subgraphs sharing a similar subgraph structure. Well, using these two trade-offs, then we combine them together with a mentor ensemble. Then we see that we could achieve, use this combined model, achieves both high accuracy and high coverage. By some evaluation results on the Scopes real workload data, we can see that the learned cost model, especially the combined one, is accurate and robust and could improve both the benchmark and the production jobs, the processing time, the query plan quality. Okay, another work is how to steal Scopes query workload, steal Scopes query optimizer. Well, first, Scopes query workload, we can see that only a very few minutes of a very few queries last a long time, but they all consume most of the resources. For the Scopes query hint set, we have more than 200 rulers in total, and some are used. And typically, we use 10 to 20 rulers. So we need to learn how to turn these rulers. Well, this space is very large. We may need to turn more than 200 rulers, and it's very expensive in execution for the model tree. So we may need to solve this problem. That is, how to find suitable rulers or hint sets for each job to steal Scopes query optimizer. Okay, here is the method of overview for this paper. Its method is like that. First, we run some query workload and discover the ruler configurations using just a random search to see which ones or which rulers should we look at. And then we select some candidate ruler configurations that is could exactly improve the runtime. And then we extrapolate to other jobs by using a learning models and deploy and test. First, we find a number. We just search different ruler configurations using some randomized heuristic search. And then we try to see that from these examples, we can see that by turning the ruler configurations, we can truly find some ones that do improve the running time. Where different rulers will correspond to different code paths in the query optimizer. So sometimes it could generate better plans. Then we could analyze that. In which cases do we turn the ruler configurations could improve the query optimizer's performance. There are three typical cases. First is that we just enable some off by default rulers is not enough. Sometimes we may need to enable more. And sometimes is that here correspond to this is that we can disable some rulers that could prevent bad code passes. And sometimes we may use the alternate rulers would be better. But this is just summarized from the sample workload, how we extend to unseen jobs. That is, we need to use the learning techniques. Okay, so we just divided the job into different groups. Well, for each group, they just share the similar code path in QU, so they could be optimized together. Then we're using just a simple regression model with the input features of the job graph and the output to the normalized running time with just a lightweight model with one layer of neural network to train this model. We can see that with online deployment, we can learn to how to turn the ruler sets, and there are large improvements and small regressions. Well, until now, we introduced two customized applications on deploying the query optimizer in real-world scenarios. Next, we switch to the more general case to see the actual deployment challenges at our general tool. Now let's switch to my colleague, Andreas. He will introduce this part. Okay.
Yes, hello, thank you very much. Let me just take over the slides. Okay. Everything okay? Video quality okay? Slides are visible?
Okay.
Okay, wonderful. So yeah, we've seen lots of interesting models and methods that have been researched. And so integrating learned components using machine learning into databases sounds great, but I guess everyone who has at least once deployed a machine learning model into production probably knows that it's much more complicated once you work in the real world. And I think this makes it also more difficult in the case of mission critical systems such as databases, which are everywhere and which are the core infrastructure components for most enterprises. So obviously the key issues we're dealing here, some examples are, machine learning models are brittle in general. It's hard to detect whether you have a failure or not because just some numbers change. Model training is not a well-defined process. You start at some point and then you at one point decide it's okay, but can you automate it? Is that okay? Then we have all the dependencies that come along with the modern ML stacks, just starting with Python, going through frameworks, going through C++ code down to BLAST libraries, CUDA kernels and whatnot. Sometimes models get deployed in external services behind Docker, because of that. So that is obviously an issue that needs to be managed in a real life setting. And of course, we need to somehow keep track of all the training data, model versions, etc. So basically everything that's sort of nowadays called ML ops. So to understand this a bit better, let's talk a bit about the general differences in these two worlds that we have. So we have databases on the left-hand side, we have machine learning on the right-hand side. So as I've mentioned, databases, especially relational databases, have been around basically forever, decades, and they're now the central fundamental piece of IT infrastructure for pretty much any business. I mean, just think about a bank or something like this. And so obviously you want rock solid, reliable, stable behavior, and most of all, deterministic behavior. You want to have the same behavior for the same query when you run it twice. On the other hand, we have machine learning or machine learning models where you produce predictions using probabilistic methods. And you have a pretty wide range of failure modes. It's inherently stochastic, so you need close supervision. So how can we make sure these two worlds can go together? How can we deal with, how can we first of all get a model into a database, like especially how to retrofit an existing database, and at the same time make sure that it's that we don't screw up, the entire business. So obviously for that, we do believe it is possible to resolve this conflict, but this requires actual proper software engineering techniques. So we need to derive some requirements. So obviously we'd want the whole machine learning part separate from the core system. We don't want to introduce any forks. We need to make sure SLAs and licensing agreements, whatnot, they're not affected. We want to reduce the amount of third-party dependencies. We want a general like array of non-functional requirements that you encounter in enterprise context: robustness, stability, fault tolerance, etc. And when it comes to the concrete machine learning related requirements, we want the usual stuff. We want to support a wide range of models. In the particular case of database stuff, we want to keep the training outside of the core system since it's not really well defined, but we still want to support the model development as best as we can. And at the same time, when we integrate any model, we need to make sure that there's a fallback, in case the model runs amok and you don't have a timeout set or your query plan, becomes complete rubbish and so on. And from different user perspectives, what this means is obviously actual users shouldn't really have to care about this at all. The DBAs, like you can imagine some gray-beard guys guarding a server with 2 German shepherds and I don't know, a sword or something like that. They probably only want to learn a few more extra config knobs, management commands, and they don't want to be responsible for managing any models or external services with the models. And opposed to that, we have model developers or researchers like us who want to, quickly get training data, quickly iterate on models, have a well-defined packaging procedure and so on, and have ideally some form of ML ops. So to kind of resolve all this conflict, we have actually developed or are developing our own system, which is called Baihe, which is mostly meant as a design blueprint for how to retrofit a system like Postgres with the various things that we've seen in this tutorial. And we are currently producing a demo implementation based on Postgres, although the principles should be applicable in general to other systems. We hope to open source that soon as a sort of research-oriented MVP. Basically, the key features of this concrete implementation for Postgres is that it uses the very idiomatic usage of basically Postgres' architecture, meaning we chose to have models running in extra background workers which communicate using the backend where our extension lives, using shared memory. We have a complete separation of the Baihe system from the actual Postgres host system. And in terms for when it comes to the query planner, what we do here is we actually create a shadow planner, a duplicate of the planner inside the extension, so we don't have to mess with the core planner code. And we make heavy use of shared memory, both for the communication part and the data collection part for training data. And to make everything smooth and sort of nice out of the box experience, we have an entire Python support library, which we basically use to train and deploy models. And it's probably best if I just start by showing the demo. It's a pre-recorded video, which I'm going to start now to make everything a bit more plastic and visible. So let's see that it works. We currently have a preprint white paper up on arXiv where there's more details about this, and which is still in a draft stage. There's the link. Okay, I really hope it's going to work. Let's see. Please let me know if you don't hear anything in the video.
Hello, everyone. Welcome to the demo part of our tutorial. I will show you now how we can use Baihe to train and deploy a simple query runtime prediction model. So Baihe consists basically of a C extension for Postgres, plus a Python support library, plus a number of stored procedures and UDFs, which are part of the extension for Postgres. And we will use that now to deploy our model. Everything is self-contained here in a Jupyter notebook. So that way it's much easier for you to follow, hopefully, and to see how all the components work together. So let's connect to the database. And now we define a data collect. which will make sure that we collect all the query plans and runtime statistics for select queries which touch these tables, which are part of the stats benchmark for cardinality estimation. So this data collector is defined. Now we start it. Once it is started, it will trigger saving all this training data in shared memory across all backends which are connected. So now obviously we have to collect training data, and for that we have to run a bunch of select queries. These are all from the stats workload for cardinality estimation. This will take some time, so I will pause the recording now, and then we can get back to it once that is finished. All right, all the queries has been executed. I'm back. So now all the collected data resides in shared memory. So we obviously want to start the data collector first and save all the memory in a table where the data set will be versioned. Okay, that's that. Let's make sure we have the data set. Okay, we have it here, version 6, 106 queries in there. Now it's time to train our model. Just 1 second. And there we go. So obviously first we have to write some basic featureization code to turn plans into vectors, query plans into vectors. That's just a very, very simple example, nothing special, just get all the cardinalities out of the query plan. Now we can define a simple model using scikit-learn, in this case a random forest regression. We use a featureization that we just implemented and get the data using our Python support library, which will get the latest version of the data set from the database. And then we get our query plans, and as labels we use the runtime. We train that model. That was very fast, of course. We just verify that the model produces something meaningful. Okay, that looks okay. Cross-validation mostly okay. Maybe some issues there, but that's only for educational purposes. Let's see what it looks like, and it looks like we basically hit the same ballpark using our prediction. So let's keep that model for now. It's time to deploy it. So to deploy the model, we have to package the model itself, meaning the saved weights and the pipeline definition, all the code, including the featureization, into one package and deploy it to our Python and Postgres instance. Right, so let's export the model first. In this case, we'll just use joblib and save everything pickled, load it again, make sure it works. Okay, that looks enough. All right. So it's time to package it. So in general, for most projects in the machine learning space, your directory structure will look something like this. You have some training code, evaluation code, model definition, maybe some fancy model parts, some featureization codes, and some saved weights. So what we have to do is we have to add a Python package definition. It's a Python file. Let's see what that looks like. Basically, what we do is we define an interface similar to a shared library, which works using these annotations we get from the Python library. We need to implement an initialization function for the model, and one function which actually calls the inference. And obviously the reason we need to use all these annotations, etc., is so that the Python part on the server, meaning the embedded interpreter, knows how to use our model, knows the input and output data types, etc. In this case, the wrapping code is here very little. We just have to load the model again from the file, which is part of the package. We have to get the query plan here, deserialize it, then call the model prediction function. That's pretty much the definition of the interface. And then to build and actually package everything, we have two functions from Python called build and deploy. So these are run if we just execute this function on the command line. So let's do that. Okay, now we assign the model ID runtime basic, and we can see that the code picks up all the dependencies for a model, meaning code and data, and then uploads it directly through the standard SQL connection into a large object storage on the Python plus Postgres instance that we're running. Let's check that the model made it into the system. Yes, we have the model here with the ID in version 1. All right, now it's deployed. Now we need to tell our database to actually use it. All models inside Python run in a background worker. We can start and stop these background workers using stored procedures. And then we also have to tell the system to use our model for the runtime prediction, which we do here. We don't need these guys here. Actually, that was done earlier then. So we tell it to enable runtime prediction. We choose the runtime model and the specific prediction function. So we could add several functions actually to our model in case it has like different kinds of functionalities of it. So let's do this. Okay. Let's hope our model runs. We could check the logs, but it should probably work. By default, the runtime prediction is integrated into the explain functionality. So let's run an explain query, explain for a simple query. And there we go. We get a runtime prediction of about 8 seconds from our model here. And now let's see how that compares to the actual runtime. It's a few seconds. Yeah, okay, but it's okay. We have here 4 seconds actual executing time and 8 seconds predicted. So it's roughly the same ballpark. It's probably enough for our demo purposes here. And that was pretty much the entire process, going from the training data through the model, writing development itself, model packaging, and deploying it into the system. So everything inside here was happening in a Docker instance based on the official Postgres 13.1 Docker image. So, okay, that was the runtime prediction. We can do something very similar for the cardinality estimation case. So in this case, I'm not going to execute and train it in here because the model is based on PyTorch. Training will take some more time, and time for that tutorial is a bit limited. So in this case, I'll show you what the package definition would look like if we were to deploy the MSCN cardinality estimation model proposed by Andreas Kipf. Here, obviously, we have a dependency on PyTorch, which is no problem because our embedded interpreter uses it. We import a lot of stuff specific to the MSCN model. We have some custom code for loading data beyond the PyTorch checkpoint, like embeddings for the tables here. And in our prediction function, where we receive as input basically a list of query predicates, we have a lot more data wrangling code until we can finally actually call the model and return the predicted cardinality. So obviously you could see one of the reasons why we kept an embedded Python for the deployment part inside Postgres, because it just makes it so much easier to deal with all this data wrangling, reformatting, serialization, etc. We built and deployed a model. We have to change the configuration slightly to activate it. And then basically, once we run a query like this from pSQL and set the log level a bit higher, we can see that where can you see it? Here is the model MSCN. that is called, and it receives a rough estimate for the result set size. It also works for the multiple table case. In this case, it would probably call the model a few times for a number of subgroups. So what was it? That was the demo part. I showed you how to deploy a very simple model using Python for runtime prediction. I also showed you how to deploy a bit more complicated PyTorch-based model for cardinality estimation. All of this is completely self-contained inside Python. No changes to the Postgres source code. Just install the extension and you're ready to go. That's it. Thank you very much. Looking forward to interesting Q&A. Bye.
Okay.
Hello, everyone.
So let's stop the video. Okay, that was the video and the demo. That concludes my part. So we'll have basically a summary now by Zhurong, and then we're finished and can go into Q&A. Okay, just let me, where is that? Yeah. Okay, thank you very much.
Okay, finally, let me make a short summary and then we come to the QU part. Well, in this tutorial part, we can see that QU is a suitable experimental plot for AI for DB, and we have witnessed many learned query optimizer techniques in recently. For query optimizer component, cardinality estimation, cost model, and join order selection, they have proposed many methods. They exhibit advantages, but admittedly, they are still not ready for the actual deployment. Yeah, and for the learned query optimizer module, we have learn to replace original query optimizer or learn to steal an existing query optimizer. Some possible way is also identified, but it is far away from a desirable learned query optimizer. We can also witness some applications and of the query optimizer, some attacks on customers, systems, and tasks. And we note that the general deployment tool is very necessary, and our Python system make taking the first step. Well, in the future, our final goal is to achieve a practical and intelligent query optimizer and beyond. We still have a long way to go in the future work. And we witness that for the cardinality estimation, maybe a fusion of the data-driven and query-driven methods would be helpful. And we also need to develop some adaptive methods that is adaptive to both different query workload, OLAP, OLTP, and different data. And we need to consistently improve the performance in terms of the update speed, accuracy, especially on multi-table queries, and the awareness of different subqueries. For cost model and join order selection, we'll need to automatically generate sufficient training data with large covariance to design more robust models for dynamic workloads and intelligent algorithm selection given workload and data sets. For the query optimizer learn whole module, we may further developing our pre-training and fine-tuning techniques routine and may design new architecture to better steer existing QU to improve its performance setting and new training and update strategy. In terms of the application developer part, maybe more general deployment tool and more customer turning applicable on different existing DBMAs. Beyond the QU, we also seek that we could extend our these techniques to more AI for DB or even some DB for AI tasks, such as indexing, adversarial, diagnosis, and etc. Okay, this is our content of our tutorial, and this is our speakers. You can contact us with such email, and let's work together for much better learn to query optimizer and AI for DB. Now let's come to the QA part. Okay.
All right. Thank you to all the speakers for the great presentation. It was very, very interesting. I believe that there are already a few questions lined up. I remember Temis had one in the first part, but the floor is open. You can directly unmute yourself or write in the chat or write to Slack and I will read them.
Yes, if I may go first. Thanks, Paulo. So one question regarding, if I remember well, slide 14 of part 2. So you mentioned a scheme or a technique called DFS that's supposed to help with learning from data that change over time. So I was wondering if you could say a bit more about this.
Okay, for data part 2, you may want to is on cost model or a cardinality estimation?
Yes, so this part.
Which part? The cardinality estimation part or the join order and cost model part, they are very different.
I think cardinality estimation, so I don't remember well, it was part 2 in your tutorial, slide 14.
Okay, okay. Could you repeat a bit? Okay.
So if I remember well, you mentioned that there is this technique called DFS, which can help in learning in the cases where the schema changes over time. So I was wondering what this DFS is.
Okay, I know your question. I think this is related with Chen Liang's part, but he's I'd be sorry that he's absent. I would recommend you you can send him an email and I will ask him later to respond to your question. Okay.
Okay, thank you.
Oh, hi, can I go first? Sorry, can I go next? This is Arun from Huawei.
Please, Arun.
Yeah, thank you. So my question is about the models that these techniques learn. Okay, so here is the question. So imagine you are doing machine learning to classify images. Okay, and you have built model using, let's say, some ready-made technologies available from PyTorch. And the model that you have created at various layers, because it's a visual task, you can say that, okay, at first layer, model is recognizing, let's say lines. On the second, at the second layer, it is recognizing, localized shapes and so on and so on, right? So we have some understanding of what's happening at every layer of the neural network. So now bring this problem to the database QO world. So the models that you guys have built, and anybody can take this question. So what have they exactly learned? I mean, I can guess what they have learned, but did you guys investigate what the model ended up learning?
Oh, well, this is a very, very good question. Well, admittedly, we should know that I think for especially the deep neural networks, for the deep models, explain what the model learned is not slowed. And I think it would also be a long-standing problem. So in the query optimizer, I think at our unknown stage, most of the learned techniques are just try to apply and use existing deep models, but not concentrate on what the models exactly learn. But I think that this would need to be very important and need to be investigated deep if we could want to make the learned models more applicable and deployable in real-world DBMAs. Well, we could also step a bit along this direction, and we could share some our experience. Okay, in fact, what our experience is that for statistical models, we know much better of what it learned. For statistical models, what we learn may be the data distribution and the mapping relation from the query predicates to the data, for example, or which data it accessed or somewhat like this. For deep models, such as the tree convolution network, it is not clear yet, but sometimes with some inductive bias, we know that it tries to learn some maybe some general rulers on how some mental rulers on how different operations and different operations act on with different canalities and with each to some cost, something like that. But the explainability is not very good. So admittedly, I recommend I recommend to using more explainable models in nowadays AI for DB, especially in QU. For example, we witnessed that the Bayesian network and our explainable model SPN and our FSPN is made much more better and safe. Okay.
Yeah, thanks. I mean, this is a general machine learning shortcoming. So I think nothing to do with this problem as such. This is a general machine learning problem. So, so you guys, I think in the Bao paper, you guys did write something about this by saying that it seems to learn that, let's say, I mean, I don't remember exact example that you gave, but it learned something like this. So let us take a nested loop join. So
we didn't write the Bao paper. We didn't write the Bao paper. We did that.
Yeah.
I said IT. Yeah, we didn't do
that.
So
somebody else. Okay. So still okay. But I guess the sort of the question is more general anyway. Okay. So I mean, I'm not asking sort of a Bao question, but so I think. So generally, I think what it seems to have learned is, so let us say nested loop join. A good nested loop join is one with a inner side having a index access. Index is available on the inner side, and outer side, is the probe side. So that's a good pattern. So I think hopefully the machine learning model learns that, so like a good nested loop join is the one which is of this kind. Okay, so this is the kind of thing that, let us say, tree based convolution network should learn, right? But I mean, do we have any evidence of that, that happening?
Yes, in fact, what I think I agree with you that what the Bao paper tries to learn in the tree convolution is some maybe mental rulers such as nested loop join with index or merge join on top of a merge join would be better. For the evidence, in fact, we do not identify we do not identify much of which evidence, because it's exactly is general deep models. It's very hard to analyze what the weights represent. Okay.
I mean, personally, I would very much recommend, be very happy if any junior researchers, PhDs, or like master projects would work on explainability for models used in database context. I think that's a bit of an open question. Yes.
Yeah, thank you.
Any other pending question? So while you guys think about your questions.
I have a question.
Oh, great. I will keep mine for later. Go ahead.
Okay, so I'm Ulf from Humboldt University in Berlin, Germany. I think at the beginning of the second part of the tutorial, you mentioned a project, I can't remember the name, where you said that in this project, you sort of learn a big background model and then try to have a concrete workload, or to model a concrete workload as a fine-tuning step on this background model. Did I got this right?
In fact, this is not in the part 2. I think it's in our part 3 on try to learn a module for the whole QU module.
Yeah, so it was in the second half of the tutorial. I don't know about your part.
Okay.
But so when you mentioned this, I was wondering how this could work, and let me explain why. So I know a lot about fine-tuning, and it's very popular in the language world, right? So when you do NLP, you build a background model, and the background model essentially learns, in a way, the semantics of individual words or word pieces, and then you try to fine-tune this large semantic model reflected in a few 100 million parameters based on a concrete setting, text classification or whatever. But this model is, so it has two assumptions, I think. The first one is you have an almost infinite amount of training data. So because you can generate essentially an infinite amount of language examples by scanning all books and scanning the web and whatever. So that's the first. And the second is that it is based on the idea that a language consists of words, and that these words carry context-dependent semantics. So there's something very common in our language. We always use the same words. And this is what the background model learns. But now when I try to translate this idea into databases, and you seem to mention a project where it works, I was puzzled, because when you think of a database of movies and the database of salaries or whatever, there's just absolutely nothing that they have in common. So I wouldn't know what a background model should learn in this.
Okay.
What this background model could learn.
Okay, let me explain a bit. Maybe agnostic, our technique cannot extend to the so complex database on movies or images, something like that. Please just concentrate maybe on the categorical or continuous attributes. Well, for example, I think what we target to learn, we have analyzed before, is we try to learn the distribution of the joint attributes. Well, just the proof of the data distribution. They may have different correlations, different skewness, different types of distribution. What we learn is the form of the distribution. If we have seen enough different types of data, we will see different distributions. For example, it may dense, they may sparse, there's some part, and we may just summarize it into some mental rulers to see with each type of distribution how we do card east. Are they independent or not independent? How to we do card cardinality estimation at different distribution, how we do joint order selection, how we do cost models on different distribution. Here what we know, we learn exactly is just the general form of the distribution. I think that's a bit different from the language models, because it's just an abstraction of the data form. But for language, it's more specific with the words and sentences and with their semantic meaning. So by this assumption that we, I think we could maybe just neglect the specific of what underlying data represents. It may represent the salary or age. We just regard them as numbers, and the distributions is what we learned. Okay.
Yeah, but even if it's distributions, I mean, so are you assuming that there is like a finite, not so large number of different distributions all over the world for whatever kind of attribute, and by having a large enough model, you have an example of each and every of these distributions? So what do you learn when you have a distribution of the height of people, and when you have a distribution of the pressure in the German water pipelines? So yes, I don't see the relationships.
In fact, if they do not need to have any relationships, but in fact, all the distributions, if we normalize together, they are just a curve. They are just a specific curve, and along some interval. In fact, they share some similarities. We make a split, and if the large model has witnessed enough examples, it may know that okay, this maybe distribution on specific data is similar to what I see before in each interval, and then I can use the same behavior to do cardinality estimation on this data part, something like that.
Okay, thank you.
Okay, thank you.
Any other question from the audience? All right. I do have one question that I think is tailored to Andreas, but I would like to hear from any of the speakers. Can you bring up your slides again, Andreas? Do you mind? There was a slide about the deriving requirements.
Oh, okay. Yeah, sure. 1 second, please.
Yeah. So my question comes from the fact that in the future work, there was some emphasis on many aspects, including improving the performance, which I guess that we all agree that it's important and it's going to make, good impact, good papers, because you are beating the state of the art. But I had a strong feeling when I saw this slide that the main challenges are in this slide and maybe in the next one, because we all like using machine learning and deep learning, but I think that Andreas with this slide was putting his finger on the challenges coming from the fact that for industrial products so stable and so reliable like databases, putting some new methods that have fantastic performance but are more brittle, it's a very risky job, right? So I wanted to ask you guys to comment a bit more on this, if you have any insight on who is
sure, I'd be very happy to.
Who is going to do this job? Because I believe that us as a researcher, we like sometimes to take the little problem where you can find measurable performance, right? While here, it's more tricky and more subtle. And just last comment, I wonder if it doesn't make sense to think about having the traditional architecture and use the deep learning, the machine learning to inform these methods and to make them more faster and more with better performance, but keeping the guarantees that they provide. Thank you.
Okay, I'll try to answer this question. Thank you very much. Basically, the background is we started this machine learning for databases work roughly 2 years ago. And what we realized at some point is, yeah, there's lots of papers, but most papers just write a bunch of Python code and do some evaluation and produce numbers, but it never even runs inside a real database. And so we gradually progressed from benchmark studies to the questions that we're a tech company. I mean, at some point we need to implement this stuff. How could this look like? And we realized that there isn't really a design blueprint or a best practice or this kind of stuff. I mean, nowadays we have that in the more, let's say, traditional web companies for recommender systems or search or like general inference APIs. There's a kind of idea how you do it, usually by hiding lots of complexity behind like containers and Kubernetes and so on. But obviously that's not possible for databases because we have to pass information and back and forth to core components, which are hopefully exposed using some API. And that was basically the start. And basically what we also wanted to say here is, especially like from my experience, having actually worked in the real world in financial institutions and so on, where you sometimes have to fill out forms just to run a query on a production database, is there stuff that you know usually you don't think about in research. I mean, it's like you can't tell your client that you know he has to use a fork of Postgres or do some, because you know maybe he relies on security patches and regular updates, and you don't want to have sudden cases where maybe you have a completely rubbish query plan, and the query takes 20 hours and your batch is basically stopped for the night and you can't do anything. And so basically based on these thoughts, we tried to derive a couple of requirements and derive it into this sort of like reference architecture here for Postgres, which to be honest is at the very beginning. So we're just starting to evaluate it. The basic system works. It's usually I guess the key point about it is to keep everything separate from the actual host system. I think that is the most important part. And to have even the models run in separate processes, so you don't run into issues with threadings or threads, or if the system locks up, you can implement timeouts. You don't have any network problems because it still runs on the same machine. And then we have, and then we have the whole issue of dependencies. Like on a production server, you can't just install like 200 Python packages because you want to run some models. So what we actually use here is a compromise now between ease of development and also like minimal requirements, dependencies is that we handcraft the Python interpreter, which has most dependencies that you need for the types of models that we're looking at statically compiled into the system itself. And in this case, it's not compiled into like the Postgres stuff. It's actually compiled into a shared library, which is mostly like self-contained. And so you don't have to tell your favorite DBA to make sure you have PyTorch nightly running on his production system. But I think it's the interesting thing about this is, and also the reason why we want to open source this, and is that I don't think there is a really clear set of best practices when it comes to what we call systems ML and how to use it in the real world. And we hope that we can push a bit, maybe the more engineering inclined researchers to work in this direction. I mean, it shouldn't just be about finding the latest, greatest TreeLSTM convolution transformer network to do something. It should also be about producing actual products. And that's sort of the key philosophy here, and maybe what differentiates us as a company from, and doing applied research from more like the pure aspects, which are equally relevant, of course. So I think that's, I hope that answered most of your questions.
Yeah. I understand that your effort with your new system is motivated by that. But do you think that the design choices that you are taking there, they satisfy all the requirements you mentioned in the previous slide?
To be honest, we don't know yet. We have a gut feeling. We're a couple of months into development. What works very nicely so far is like the whole development deployment aspect, because you write your model, you deploy it, and then you see, oh, I have a mistake. So you just change the Python code, you deploy it again. You don't have to restart the server and so on. That works relatively nice. And so the next thing that we're going to look at is to integrate a more complicated model and then see how it behaves under load, especially because we don't have basically a copy of the model running for every client. We kept it separate, so we'll have a queue, so there's be some issues with the system load, and that's going to be very interesting, I think. Yeah.
All right. Thank you. Okay, we have time for a last question from the audience. All right, so I will use these few seconds left to thank again the speakers for this very nice tutorial. Thanks for the people having bringing their questions and comments. And yes, we all thank the reviewer, the speakers, and don't forget that there is still a keynote ongoing after the next break. Okay, thank you guys. Have a good rest of the day.
Thank you, audience, and ciao.
Thank you.